All right, folks, in this video I want to talk about decoupled equations. So for this scenario that we're analyzing, we have this beam that's got a 600 Newton force applied here, 800 Newton force applied here. There's a 900 Newton meter couple moment applied at the end, and it's being held in place by a pin at A, so it's got an AX and an AY. It's being held in place by a short member BC that's putting a force on this beam as well. So a decoupled equation is just an equilibrium equation. It's like what we've been talking about. It's just slightly different in that a decoupled equation is an equation that has only one unknown in it, even if it's the very first equation you derive. So it doesn't depend on any other unknowns. And when I say unknowns, I just mean the AX, the AY, and FBC. So let's take a look at what this could be. I think a good place to start would be taking moments about point A. Because if we were to sum forces in the x direction, AX is in the x direction, and there's a component of FBC in the x direction. So summing forces in the x direction will have two unknowns. If we sum forces in the y direction, we'll have AY and some component of FBC again. So if we sum moments about A, that's going to eliminate AX and AY, and we'll just have FBC in that equation. So let's sum the moments about A, and we're going to set that equal to 0. So what's causing a moment about A? Well, this 900 Newton meter couple moment is causing a tendency to rotate everywhere, so we need to include that. It's 900 Newton meters, and I said it's negative because this is showing a clockwise rotation. Now, the 600 Newton force is also causing a tendency to rotate about A. That will be 600 newtons. 600 newtons times, that's acting at 1 meter away. And that again would be causing a tendency to rotate clockwise, so it is negative. And then we also have this 800 Newton force that is acting 4 meters away. 4 meters. Also negative because it's also causing a tendency to rotate clockwise. And then we've got FBC. Some component of FBC is causing a tendency to rotate. So we want to split this up. Only the vertical component of FBC is causing a tendency to rotate. The horizontal component has got a line of action that goes through point A, so it causes no tendency to rotate. If we look at this triangle here, this is point A, this is point C, this is point B. This is 1.5, this is 2. If we use Pythagorean theorem, we'll find that this is 2.5. This is similar to a 3, 4, 5 triangle. So to find the vertical component, I could either multiply FBC by 3 over 5, or I could just do 1.5 over 2.5. That's the vertical component, and then the distance away that it's acting is this 2 meters. So I need to do this times 2 meters. That's gonna generate a tendency to rotate counterclockwise, so it's positive. And that's it. So I can set this equal to 0. 0. From all this, I get that FBC is equal to 3920 newtons. Okay, so now that we know 3920 and we know FBC, if we were to sum forces in the x or y direction, there'd be only one unknown in those equations. Those are still not decoupled equations though, because they depend on FBC. They depend on that value. So let's find decoupled equations for AX and AY. Well, moments about A was a decoupled equation for FBC because AX and AY both have lines of action that go through point A. So if we, for instance, want to find a decoupled equation for AY, let's find a point that we can take moments about where the line of action of the other two forces, the line of action of AX and FBC, both go through that point. So if we extend this line of action this way, we'll see that moments about B would be a decoupled equation for AY because FBC and AX do not appear in that equation. So let's find the sum of the moments about point B and set that equal to 0. Again, we're going to have this minus 900 Newton meters. If we sum moments about any point, we got this value in there. If we were to sum forces, we would not have that. We're going to have plus 600 newtons, which is acting at 1 meter away, plus, because it's generating a tendency to rotate counterclockwise, minus 800 newtons times 2 meters. And then moments about B, the last thing we have is this AY. AY is acting 2 meters away. And I think that's it. We'll set that equal to 0. AY is generating a tendency to rotate clockwise. As it's shown, this AY would generate a tendency to rotate clockwise. Because it's clockwise, we're going to make it negative. When we plug this in, we're going to find that AY is equal to minus 950 newtons. That minus sign just means that we drew this in the wrong direction. That's completely fine. We're not going to change this. We're not going to change this. This just tells us that AY is actually downward. That's quite all right. We'll just leave it as it is. So this is our value for AY. So the last one, what do we need? We need moments. We need to find an equation for AX, a decoupled equation for AX. Again, I'm going to say if we're looking for AX, let's take the lines of action of the other two forces, see if they connect anywhere, see if they intersect. And these two lines of action intersect about this point, intersect at point C. Point C is not even on this object. That does not matter. We can still take moments about C. The moments about C still has to be 0. So let's do moments about C. What do we have? It's going to look a lot like moments about A. We're going to have this minus 900 Newton meters. We're going to have minus 600 newtons times 1 meter. We're going to have minus 800 newtons times 4 meters. And then the last thing we got is this AX, which is going to be minus AX times 1.5 meters. That'll be equal to 0. So AX here is going to be minus 3130 newtons. So moments about A, moments about B, and moments about C are decoupled equations for these unknowns. If we were to do moments about A and then some forces in the X and Y, we would find the same values. We're not finding different values here. It's just that decoupled equations can be useful for many reasons. One is that because each of these unknowns is in terms of only the known values, we're not going to propagate any errors through. Like if we messed up this equation, got the wrong value for FBC, if we sum forces in the X and Y directions, then the wrong value for FBC is going to make these other values wrong. If we do all of these, if we get an equation for all these unknowns in terms of just the known values, then that error propagation doesn't happen. This is also just a useful way to think about analyzing these problems. It's good to sort of understand this process in 2D because it'll help you a lot when we get to 3D equilibrium. And in this scenario, all of our decoupled equations were the summation of moments. Sometimes summation of forces is a decoupled equations. Decoupled equations aren't always moments, it just happens to be in this case. Hope this helps. Good luck.